So I'm going to show you a basic demonstration of how we can unlink identifiers. So in this presentation, what I want to do is to be able to link one pseudo ID to another pseudo ID without actually discovering what the link is. So the method that we'll be looking at was developed by Kamenish, and it's defined as CL15. The team also developed on the CL17 to make sure that it was possible to audit the accesses done within the linking process. But basically what should happen is that Bob has his own ID, and then System A knows Bob as a certain pseudo identifier, and System B knows Bob again with another pseudo ID. It is not possible to link Bob across the two systems, and Bob will have complete control of the linking between the two systems. So this could be a government record, such as his healthcare record, and this might be his tax return here. Okay, so the method involves using discrete logarithms and also homomorphic encryption. Homomorphic encryption allows us to be able to operate on encrypted values. It's a really cool technique. In this case, I'm going to use RSA to do the encryption and the homomorphic encryption, because RSA is somewhat because RSA is partial homomorphic encryption, and the method that we're applying will work. Okay, so we start off and we take the user's ID, and we have a value for system A and a value for system B. We then take Bob's ID and raise it to the power of XA. We also have a mod P that I've not shown there, but we take it to the mod P, so they end up with a finite field for that. But basically we take the user's ID, raise it to the power of XA, and this becomes the pseudo ID within system A. No one can tell what the value of UID is because of the power of discrete logarithms, or the difficulty of discrete logarithms. And then system B, Bob defines a unique identifier, which is his unique identifier raised to the power of XB value, mod P again, and that's his pseudo ID. So it shouldn't be possible to be able to link the IDs between the two systems. What we then want to do is to create a controller which creates the linking service between the two of them, but where even the controller, the government in this case, will not be able to determine the linkage and what is being linked between the two. So this paper expanded this on to define an audit trail, so that Bob could actually see who was linking the systems, the two pseudo IDs, and it would have an audit system, and even the controller wouldn't be able to link two of the same links. Okay, so I'll explain the basics behind the method. So as I said, we take the user ID, we raise it to the power of XA, and that becomes the pseudo ID in domain A, system A, and we take the user ID and raise it to the power of XB, and that becomes the ID in system B. So it's not possible to be able to trace the two identifiers there, and what we want to do is to make sure that no one can actually see the linkage between the two identifiers. So the first thing that we do is that we take the ID from here, from system A, and then we encrypt it with the public key of system B. So in this case, we'll use the RSA public key to be able to encrypt the pseudo ID that we see in system A. So then the linker can then take this value and then raise it to the power of xb divided by xa. And this is us operating with the cool method of homomorphic encryption. In this case, we can still operate our mathematics of Napier's logarithms. So if you remember that a to the power of x to the power of y is equal to a to the power of xy. What goes on here is kind of the same, but we're operating on encrypted values and we can still do this type of operation. So if we remember that the pseudo ID is equal to the user ID to the power of xa to the power of xa xb. So if we forget that we're actually dealing with encrypted values here, it still works out, and that's the fantastic thing about homomorphic encryption. So that becomes that multiplied by that. Because of the rules of logs, we cancel that and we cancel that, and we end up with uid to the power of xb. But remember, we're still dealing with encrypted values, so that the controller cannot tell what that pseudo ID actually is. So then this becomes this here. And now all we have to do is for system B to take its secret, its private key, and then decrypt this encrypted value, and then ends up with this unique identifier x ui to the power of xb, which is the pseudo identifier with inside the domain. So sample run shows that here's the values. So let's actually see if we can get this here. So we take a unique ID of 45 and an xa value of 12, and we'll take that as 9. So the unique identifier, let's take 41. Okay, so the unique identifier is 43 here, and 43 to the power of 11 is that, and to the power of 10 is that. Okay, this is the encryption keys. I've generated random p and q values to give an n value of a certain size. Using the mask that we saw, we end up with this cipher, and then when we decrypt that, we end up with the ID of the pseudo ID of B. So the actual code behind it isn't too difficult. So I'm generating values of P and Q, and then I get N. I take an E value of this, which is fairly standard, to work at 5, and that gives us our decryption key and our encryption key for system B. I then take some ID values and XA and XB. I then work out the value to the power of A, XA, and then the value to the power of XB, and it gives me my two pseudo IDs for system A and system B. I then encrypt the first value with the encryption key of system B. I print out the cipher. I then take the cipher to the power of B. This is where the homomorphic encryption is coming in. It's just an amazing method. I raise it to the power of B here, and then I divide, which is the inverse mod of XA. So that's equivalent to raising to the power of XB over XA. I then decrypt with the value of D, my decryption key, and magically the value returns back from there. So I've taken this value, I've put it through the encryption and the homomorphic encryption, and ended up with this value. So only when we get to the system B do we actually see what the pseudo ID is, and the controller can't tell. Okay, so that shows a result. We go from here, and then we end up with this ID here because of the homomorphic encryption. Okay, so that's been an outline of unlinkable identifiers using the homomorphic encryption.